All right, briefly to respond to your questions. I, one clever student graphed their energy level as if it's logistic, and it got me thinking, like, what would our energy level look like if it were logistic? We would all, first of all, we would max out. There would be a maximum amount that we could approach. We would all eventually get there at our own little different times. And I sort of thought, for some reason, it made me think of like those movies where they're in some kind of like fictitious place where everybody acts like they're happy all the time, even though that they're not happy. They like everybody walks around standing upright and smiling. Like, to me, it made me think of something like that, which is not a place that I want to live in. And I think its energy levels are much often a periodic function, which some people did, but I didn't capture any of those. Um, as far as logistic growth goes, here is a good question. Can there be other variables in the equation, or does it have to be of this form? I want to point out that in all the math that we do this year, there's only two variables. There's y and there's x. Okay. Next year, you'll introduce the concept of multivariables, and a lot of the concepts that we practice are extended or analogous with multiple variables. Like like in the real world, there's almost nothing that's measured where your dependent variable y is a function of only one independent variable. But that's what we do, is we build models so that we can get more complex, but we have to understand the roots of the models first. This R, P, and K are not variables, they're parameters. Okay, so a parameter is a number that in any particular example is a constant. So I think that's an important distinction, not for logistic growth, but just for functions in general, that these are parameters that differ based on the specific type of logistic function that you have. And once you understand the model, you can infer from the RP or the K values what the carrying capacity is, what the top of the population is, and something about the amount of time it takes. If the lower asymptote was not y equals 0, how would we know? What would the question be phrased like? I don't know. I haven't seen it. I mean, I could think of, instead of having just, where you just have, in this example, where you just have 2y, you could have maybe 2y minus 1 and then 3 minus y. And then you could picture that the differential equation between 1 and 3 is going to be positive. And so if you were to drop some kind of little drop in between 1 and 3, it would, no matter where you dropped it, it would always end up at the top at 3, because it's going to follow this path. But it doesn't have any real practical applications that I know of. So I would just think that this is almost always going to be measuring the growth of some type of population, and the population, the lowest the population can ever go is 0. Are logistic derivative equations always in the format of dy dx is equal to 2y times 3 minus y? They are always in that format, in the sense that these numbers can change, but it'll be a product of two expressions that only have a y in it. If it had an x in it, it would blow the whole thing up. If it only had one y in it, it would be exponential. So I think that's the format for these. And in that problem, there was the FRQ problem that I referred to. There was one y. There was like a part A that had one y and one x. It's not logistic if it has one y and one x. It's only logistic if it has a product of two different y expressions. Are there cases where the y coordinate or the inflection point of the logistic growth is not half of the k value, or the inflection point always half of the k value? I can't prove that it's not, but I haven't seen it, so I think it's safe to assume that it would be. What happens if 1 minus y over k is negative? I mean, you could picture it. This would be a good question for you to answer yourself. If you're curious about that, kind of play around with it and look at what happens to those slope fields, and how that distorts the slope field. And I think those are the types of things that have given us imaginary numbers, and those are the things that are applied in electrical engineering and time series econometrics models. So there probably is some application to it, but I'd be lying if I said I knew what it was. So I encourage you to go out there and experiment with yours, with this stuff a little bit.